1. The Big Bang's sound suggests Earth is in a massive cosmic void, solving the Hubble tension. 2. Unraveling the Hubble tension. Are we inside a cosmic void? 3. Is Earth trapped in a cosmic void? New evidence from the Big Bang. 4. Is Earth trapped in a cosmic void? New discoveries explained. 5. Are we floating in a cosmic void? The Big Bang sound and the Hubble tension explained. 1. The Big Bang's sound suggests Earth is in a massive cosmic void, solving the Hubble tension. Imagine being part of a vast, uncharted cosmic landscape where our entire galaxy, the Milky Way, and even the surrounding universe could be nestled within a massive, 2 billion light-year wide void. This mind-boggling concept has been proposed by researchers as a potential solution to one of the most enduring and frustrating problems in cosmology, the Hubble tension. But here's where it gets fascinating. What if the sound of the Big Bang, imprinted in the form of baryon acoustic oscillations, holds the key to unraveling this mystery? New research suggests that these ancient sound waves support the idea of a local void, which could be the Hubble Bubble that we're living in. The Hubble tension arises from the discrepancy between the measured speed of the universe's expansion, known as the Hubble constant, when using different techniques. One method measures the Hubble constant locally, while the other provides an average value across the entire universe. This discrepancy has sparked a heated debate among cosmologists, with some arguing that it's a local problem, while others propose more exotic explanations. But what if our galaxy is indeed situated near the center of a vast, low-density void? This would cause matter to be pulled towards the higher-density exterior, leading to an apparent faster local expansion rate. As research author Indranil Banik notes, a potential solution to this inconsistency is that our galaxy is close to the center of a large, local void. This void would need to be enormous, with a diameter of around 2 billion light-years and a density about 20% lower than the average matter density of the universe. While this idea may seem far-fetched, it's supported by observations of the local universe, which reveal a lower density of galaxies compared to neighboring regions. However, this concept challenges the standard model of cosmology, known as the lambda cold dark matter model, which predicts that matter should be evenly distributed throughout the universe. The new research presents a compelling case for the local void theory, using baryon acoustic oscillations as a standard ruler to chart the cosmic expansion history. By analyzing these sound waves, the researchers found that a void model is about 100 million times more likely than a void-free model. But here's the part that most people miss. The implications of this discovery are profound and could revolutionize our understanding of the universe's expansion history. The next step for researchers will be to compare their void model to other models, using cosmic chronometers like galaxies to reconstruct the universe's expansion history. This could involve observing stellar populations and measuring the age of galaxies, which can be used to determine the expansion rate of the universe over time. As we continue to explore the mysteries of the cosmos, we're reminded that the universe is full of surprises and that the truth is often more astonishing than fiction. So, what do you think? Are we living in a vast, cosmic void, or is this just a clever explanation for the Hubble tension? Share your thoughts and join the conversation. The research team's findings were presented at the Royal Astronomical Society National Astronomy meeting, and their work is sure to spark a lively debate among cosmologists and astronomy enthusiasts alike. Join the discussion and stay up to date with the latest space news and discoveries. 2. Unraveling the Hubble tension. Are we inside a cosmic void? #, #, #, a groundbreaking study that could unravel one of the universe's greatest mysteries. Imagine this. Our planet, along with the Milky Way galaxy, might be nestled within a vast cosmic void, a colossal, enigmatic gap in space. This intriguing possibility suggests that the expansion of the universe in our vicinity could be accelerating at a rate different from other regions. This compelling theory was put forth by researchers at the Royal Astronomical Society's National Astronomy Meeting (NM), held in Durham. This hypothesis could shed light on one of the most perplexing issues in cosmology, the so-called Hubble tension. This term refers to the discrepancy observed between two distinct methods of measuring the universe's expansion rate. Understanding the Hubble tension. The Hubble constant, named after the astronomer Edwin Hubble who first articulated it in 1929, quantifies how quickly the universe is expanding. This rate is determined by observing how fast galaxies are receding from us and their respective distances. However, there's a significant twist. When scientists analyze data from the early universe, like measurements from the cosmic microwave background (CMB), they find a slower expansion rate compared to measurements derived from more recent, local observations. This inconsistency is what we refer to as the Hubble tension. Indranil Banik, a cosmologist from the University of Portsmouth in England and one of the authors of the study, posits that this discrepancy could be explained if our galaxy is situated within a massive under-dense region of space. A potential solution to this inconsistency is that our galaxy is close to the center of a large, local void, Dr. Banik elaborated. He further explained, this would cause matter to be drawn by gravity towards the denser outer regions of the void, resulting in the void becoming increasingly empty over time. As this void empties, the speed at which objects move away from us would appear greater than if the void were absent. This creates the illusion of a faster local expansion rate. In simpler terms, if we are indeed located within a vast low-density area, it could create the impression that space is expanding more rapidly in our neighborhood than in other parts of the universe. This theory could resolve the Hubble tension without necessitating a revision of the fundamental laws of physics. Dr. Banik added, the Hubble tension is primarily a local phenomenon, with scant evidence suggesting that the expansion rate contradicts expectations in standard cosmology when looking further back in time. Therefore, a local solution, such as a local void, is a promising avenue for addressing this issue. Visualizing the void. For this theory to hold water, our solar system would need to be positioned near the center of a void that spans approximately 1 billion light-years. Evidence from direct galaxy counts supports this idea. Astronomers have observed that our local region appears to have fewer galaxies compared to neighboring areas of the universe. Yet, this concept is not without its controversies. The prevailing cosmological model assumes that matter is distributed relatively evenly across such vast scales. A void of this magnitude and depth challenges that assumption. The echoes of the Big Bang. Further backing for the void theory comes from baryon acoustic oscillations, BOs, often referred to as the sound of the Big Bang. Dr. Banik explained, these sound waves traveled for a brief period before becoming frozen in place once the universe cooled sufficiently for neutral atoms to form. They serve as a standard ruler, allowing us to measure the cosmic expansion history. According to Banik, BO measurements exhibit slight shifts in a universe characterized by a local void. The gravitational influence of such a void adds a minor redshift to the light emitted by distant objects, in addition to the redshift caused by the universe's overall expansion. By analyzing all available BO measurements from the past 2 decades, we demonstrated that a void model is approximately 100 million times more likely than a void-free model, which is designed to align with the CMB observations made by the Planck satellite, known as homogeneous Planck cosmology. What lies ahead? To further investigate this theory, astronomers plan to compare the void model with other independent methods of measuring the universe's expansion, such as cosmic chronometers. These involve studying ancient galaxies that have ceased star formation. By examining the types of stars within these galaxies, since massive stars have shorter lifespans, scientists can estimate their ages. By correlating these ages with the galaxy's redshifts, researchers can determine how much the universe has expanded while the light traveled to us, providing another perspective on cosmic expansion history. If future observations continue to support the void model, it could fundamentally alter our understanding of our position in the cosmos and reveal just how unique our corner of the universe truly is. Do you have insights on a science story that Newsweek should explore? Or perhaps questions about stars? Feel free to reach out at science@newsweek.com. #reference. Banik, I. Desmond, H. Valentino, E.D., and Shanks, T. 2025. Theoretical and Observational Approaches to the Hubble Tension. National Astronomy Meeting 2025, Durham University. https://conference.astro.dur.ac.uk/event/7/sessions/90/20250709. 3. Is Earth trapped in a cosmic void? New evidence from the Big Bang. Imagine discovering that Earth, along with our entire Milky Way galaxy, might be trapped inside a colossal cosmic void, an enormous region of space far emptier than the surrounding universe. This startling idea comes from recent scientific claims based on analyzing the faint echoes left over from the Big Bang, the event that birthed our universe. According to these findings, our galaxy could be drifting within a vast 2 billion light-year-wide bubble that is about 20% less dense than the cosmic average. But here's where it gets controversial. If this is true, it could dramatically change how we understand the universe's age and help resolve one of the most puzzling mysteries in cosmology today, known as the Hubble Tension. The Hubble Tension refers to the conflicting measurements of how fast the universe is expanding. Observations show that the distant universe appears to be expanding more slowly in the past compared to the faster expansion we observe nearby today. This discrepancy has left astronomers scratching their heads for years. The new research, presented on July 9 at the Royal Astronomical Society's National Astronomy Meeting in Durham, England, suggests that this cosmic void might be the key to explaining these conflicting measurements, and if confirmed, it would force scientists to rethink many established cosmological models. So, what exactly is the Hubble tension? Over the last decade, astronomers have been caught in a growing debate because two primary methods of measuring the universe's expansion rate, called the Hubble constant, don't agree. The first method involves studying tiny temperature fluctuations in the cosmic microwave background, CMB, the afterglow of the Big Bang that formed roughly 380,000 years after the universe began. This approach, which aligns well with the standard cosmological model, estimates the expansion rate at about 67 kilometers per second per megaparsec, km/s/mpc. On the other hand, the second method looks at closer cosmic distances using pulsating stars known as Cepheid variables. These stars act like cosmic lighthouses, helping astronomers measure distances within our local universe. Surprisingly, this technique yields a higher expansion rate of approximately 73.2 kilometers per second per MPC. While the difference might seem small, it's significant enough to challenge the foundations of our current understanding of the cosmos. Some scientists have even proposed radical ideas, such as discarding the concepts of dark energy and dark matter to explain this tension. But the new study offers a different perspective. Lead author Indranil Banik, an astronomer at the University of Portsmouth in the UK, suggests that the discrepancy might be due to our galaxy's unique location near the center of a massive, underdense region, a cosmic void. If we are inside such a void, Banik explains, gravity would pull matter toward the denser edges, causing the void to become emptier over time. This gravitational effect would make the local expansion inside the void appear faster compared to denser, more distant parts of the universe, potentially explaining the conflicting Hubble constant measurements. The idea that our cosmic neighborhood might be less crowded than others isn't entirely new. Back in the 1990s, astronomers noticed fewer galaxies in our local universe than expected when compared to more distant regions. This observation led to the concept of the local hole, or the KBC void, named after the initials of the researchers who studied it. However, some skeptics argue that this apparent emptiness could be filled with objects that don't emit light, making the void less empty than it seems. To investigate further, Banik and his team analyzed 2 decades worth of data on baryon acoustic oscillations, BOs. These are pressure waves generated in the early universe shortly after the Big Bang, which became frozen as the universe cooled and neutral atoms formed. BOs act like a cosmic measuring stick, allowing scientists to track how the universe has expanded over time by observing the distribution of galaxies. Banik explains, These sound waves travel briefly before freezing in place, and their angular size serves as a standard ruler to map cosmic expansion history. Their analysis showed that it's 100 times more likely that we reside within a vast cosmic void rather than a region of average density. Looking ahead, the researchers plan to compare their void model against other cosmological models to determine which best fits the universe's expansion history. They will also explore adjustments to the standard cosmological model, including challenging the long-held assumption that matter is evenly spread throughout the universe. The implications of this research are profound. Not only could it reshape our understanding of the universe's behavior, but it might also redefine our place within it. Modern astronomy has often emphasized that our vantage point in the cosmos is unremarkable. Yet, if we truly live at the center of a massive void, our cosmic neighborhood might be far more unique and isolated than previously believed. So, what do you think? Could this cosmic void be the missing piece to the Hubble tension puzzle, or is it just another twist in the complex story of our universe? Are we truly in a special spot in the cosmos, or is this just an illusion created by the limits of our observations? Share your thoughts and join the conversation below. 4. Is Earth trapped in a cosmic void? New discoveries explained. Imagine this. Our entire solar system could be floating in an enormous cosmic desert, surrounded by an eerily empty billion-light-year-wide bubble in space. New research suggests Earth and the Milky Way might reside within such a giant void, a concept so bold it could rewrite our understanding of cosmic expansion. But why bother? Because this void might hold the key to solving one of cosmology's biggest puzzles, the Hubble tension. Here's the story behind this cosmic detective work. The Great Expansion Conundrum. Astronomers have faced a puzzling inconsistency for decades. When measuring the universe's expansion using faraway galaxies and stars, the speed calculates to a slower rate. But when observing nearby cosmic activity, the expansion appears faster. This discrepancy, the Hubble tension, has left scientists scratching their heads. It's like trying to solve a mystery with two conflicting clues. The void hypothesis. Dr. Indranil Banik and his team propose a radical solution, our location within a vast cosmic void. Picture this. If we're near the center of a region where galaxies are 20% less dense than average, gravity's influence would push surrounding galaxies toward the void's edges. This gravitational tug could make the local universe appear to expand faster than reality. Banik compares it to sliding objects across an icy surface. Friction effects perceive speed. How they found the evidence. To confirm this theory, researchers analyzed baryon acoustic oscillations, BOs, cosmic ripples from the Big Bang's pressure waves. These ripples act like cosmic measuring sticks, helping map galaxy distributions. Over 20 years of data showed consistent patterns suggesting a vast underdense region. But here's the controversy. If true, this challenges our assumption that the universe is uniform on large scales. A lonely universe? Proponents argue the void could explain why local measurements show faster expansion. But critics might counter. Does a billion light-year-wide empty space really exist in a supposedly uniform universe? The real test lies ahead, how this void affects other cosmic phenomena. For now, the data aligns with the void theory, raising questions about our place in the cosmos. What do you think? Could we truly be cosmic pioneers in an interstellar desert, or does this void theory hit a wall against established models? Share your take. Are we in the void, or is there another explanation waiting to emerge? 5. Are we floating in a cosmic void? The Big Bang sound and the Hubble tension explained. Imagine a universe where the very fabric of space itself seems to be stretching at different rates, depending on how you measure it. This paradox, known as the Hubble tension, has puzzled cosmologists for years. But here's where it gets controversial. Recent findings suggest that our Milky Way galaxy might be floating inside a colossal void in space, which could be the key to resolving this mystery. The evidence comes from sound waves, or more accurately, the echoes of sound fossilized in the arrangement of galaxies throughout the cosmos. These cosmic ripples provide a new level of precision in measuring the expansion of space-time. According to these measurements, our galaxy could be situated near the center of a massive void, a region of space that is significantly less dense than its surroundings. This concept is intriguing because different methods of measuring the Hubble constant, the rate at which the universe is expanding, have yielded conflicting results. For instance, studies based on the cosmic microwave background radiation and baryon acoustic oscillations suggest a Hubble constant of around 67 kilometers per second per megaparsec. In contrast, measurements using nearby celestial objects like Type I supernovae and Cepheid variable stars indicate a higher value, closer to 73 kilometers per second per megaparsec. Astronomer Indranil Banik from the University of Portsmouth in the UK proposes that the discrepancy could be explained by the influence of a local void. He explains, if our galaxy is near the center of a large void, gravity would pull matter towards the denser areas outside the void, causing it to appear as though the universe is expanding faster locally. A void in intergalactic space is essentially a vast, nearly empty region. Matter in the universe doesn't distribute uniformly. Instead, it clumps together in clusters and superclusters, leaving behind sparse areas we call voids. The idea that our galaxy resides within one of these voids offers a plausible explanation for the Hubble tension. To test this hypothesis, Banik and his team turned to baryon acoustic oscillations, BO, ancient sound waves imprinted on the cosmic microwave background during the universe's infancy. By analyzing 20 years of BO data, the researchers found deviations from the standard cosmological model that align with the presence of a local void. The BO patterns are slightly distorted by the gravitational effects of a local void, Banik elaborates. This distortion increases at greater distances, providing a clear signature of a void's influence on the observed expansion rate. Their analysis suggests that a void model is about 100 million times more likely than a uniform model that fits the cosmic microwave background data. While further testing is needed, these findings offer a promising avenue for resolving the Hubble tension. The team plans to continue their investigations by examining local space for additional evidence supporting the existence of a void. Their research has been published in the monthly notices of the Royal Astronomical Society and presented at the Royal Astronomical Society National Astronomy Meeting 2025. So, could the answer to one of cosmology's biggest puzzles lie in the emptiness of space? Only time and more data will tell. What do you think? Could our galaxy indeed be floating in a cosmic void?